Okay, so if we have a set of vectors, so a specific set of like P of them in Rn, so there's not necessarily n of them, and yet we know they're linearly independent. So what does linearly independent mean? They're linearly independent if and only if, when I take, oh sorry, these V's should have been made bold, right, because they're vectors. So a set of vectors is linearly independent if and only if the only way I can get to the zero vector, right? So these are all vector, vector, vector. All the V's are vectors. That the only way I can get to the zero vector is if the numbers in front of the vectors are zero, right? So all the x's, so the x of I, all the x of i's are zero. It has only the trivial solution, right? All right, so they're dependent if I know for any two of the vectors there's a relationship. So there could just be two that are related to each other, and then that makes the whole set dependent. So I often use the analogy in a classroom of, say, we have 22 in our linear algebra class. Let's say I had a set of twins. So because there's two people that are related in the classroom, that makes the whole class called dependent. So if there is any kind of relationship between any two, minimum of two, but there could be three. There could be three vectors that have a relationship. So if there's any kind of relationship between the vectors, doesn't have to be all of them combined, but any little bit of a relationship, then I know the whole set is called dependent. All right, so basis of a subspace is a set of vectors, this is a big deal, that span the subspace and that are linearly independent. So a basis is, here's the definition, a basis is a set of vectors that are linearly independent, right? So this set of vectors B are linearly independent. That means linear combination is zero only if all the numbers in front of them are zero. And that set of vectors spans the H, the subspace H. So then I can say that this is a basis, which is like saying it's an efficient spanning set. So are the following, these three vectors, a basis for all of R3? So if I put these three vectors into this matrix, or into a matrix, and I reduced echelon, I get to this. Okay, so what do I know? So are these three vectors linearly independent from what I get from this matrix? Not linearly independent vectors, right? Because there is not a pivot every column. So this is not, therefore, not a basis for R3. This set of three vectors is not a basis for R3. All right, so let's say I have a set S, and then I've got that H is equal to the span of that set S, right? So the span of those vectors, that's just another way of just stating what those vectors are. So if one of the vectors in S is a linear combination of the others, so let's just say these two are siblings. These two are related to each other. So what I can do is I remove it, and then I can still say if these were related, then maybe this one isn't needed to span the set. So this spanning set theorem is saying, okay, if you have a set and there's a little bit of a relationship, let's take out some vectors, and then I'll find a basis that way. I'll get rid of the vectors that will span the set, so still span H, and that they'll be linearly independent. And if H doesn't equal this zero space, right, if H is not just, the super trivial, then there will be some subset of this set of vectors S that will be a basis. So this is a method to find the basis. So it's an efficient basis. So the pivot columns of a matrix A form a basis for column A. So we already know how to find column A, and that's finding the pivot columns of the matrix A. And remember, we always go back to the original matrix to pick out those vectors for column A. And so to find a basis for column A, it's the same thing. So a basis is going to be the set that spans column A, and they're going to be linearly independent because we're picking linearly independent columns, the pivot columns. All right, so if I told you that this was A and this was B by doing row echelon, so I'm giving you the you don't even have to plug it in. So here's my row echelon of A right here. Okay, so let's find a basis for column A. So column A basis will be the pivot columns, so that will be this column and this column. But remember, I have to go back to the original matrix, comma 4, -6, 8. Okay, so these two vectors span column A and are linearly independent, so they form a basis for column A. All right, so now remember, column A was the easy one to find. Null A is the one that takes much more work. Okay, so I'm telling you that this is the reduced echelon. So if I'm going to solve Bx equals 0, because that's what null A means, solving it equal to 0, I'm going to have, let me just write the matrix down just so you see, 0, 1, 2.5, 1.50, and then a row of zeros, right? So because there's 4 columns, I know there's 4 variables, right? So this first row gives me x1 plus 6x3 plus 5x4 equals 0. The second row says x2 plus 2.5x3 plus 1.5x4 equals 0. Okay, so I'm going to solve for each of the basic variables, which I encourage you not to skip steps because this is so easy to make mistakes, losing variables, etc. Oops, that's supposed to be a 4. Okay, so again, this is one of the important steps, making sure you remind yourself at the outset, I do need 4 variables, right? So x1 is -6x3 minus 5x4, x2 -2.5x3 minus 1.5x4, x3, x4. So I see that there's 2 free variables. So if I factor out the x sub 3, and then if I factor out the x sub 4, okay, so let me come up here. So the basis for null A will be these 2 vectors. So it was a long time ago at the very beginning section that I talked about how when I do go find these vectors for null A, I know that they are linearly independent already. Because of the fact they've got 2 different free variables, there's no relationship between these 2, so they are automatically linearly independent. So this is my basis for null A, the spanning set.